so what do you have for this? Well, basically, HCl has got a weaker bond, and so you expect it to be a stronger acid. Stronger acids have a weaker bond. We would have expected HF to be a strong acid too. It's a weak one because of ion pair formation, was it? And so it's unusually weak, but it would have been weak. Why is acetic acid stronger than ethanol? Yeah, this is kind of go through it and summarize it in your own words is best. But there's something I don't do really. I don't really summarize it for you. And so I just want you to look through it and then come up with your own. Polarity is one. But if you look at the HO bond, the HO bond should be the same polarity, right? They have the oxygen has the same electronegativity. We're looking at the same kind of bond. You have to be more detailed. Yes, it is because of polarity, but because why? I mean, they both have the same COH link. Because of the extra oxygen, and there are three ways you could explain this. Or actually two for this particular instance. You have it?
Because I think it's oxygen, or I forgot which one it was. It takes like less electrons.
Yeah, there's a name for it. Very, very famous name for it. Well, all the electronegativities are kind of the same. It's not the electronegativity that does it necessarily. Yeah, for those of you who want to, you would go through it, after class, and then look at it. When you look at it, and then I said like a couple of different things for this particular combination, but what you would want to do is you want to summarize it, because I said there are two ways you could look at the polarity in terms of the common way with the arrows and that kind of stuff. What was that called? I think, yeah.
Inductive effect?
Inductive effect, right. There's one way you could do it is inductive effect. By the inductive effect, this acetic acid is going to have a much higher polarity because of that oxygen, right? And the other way of looking at it was what? Not the inductive effect, but by looking at the oxidation states. You can see the two carbons are totally different, right? And then that will change its polarity. So on the one hand, acetic acid is much more polar. How about the bond strength? What was more important, bond strength or polarity?
Bond strength.
Bond strength, but these two should have the same bond strength, correct? And and so there was something else that factored in. What was that? Hmm?
Stability
Stability of what?
on the solution
Stability of, there are
of the
two,
conjugate base.
of the conjugate base, right. And so we looked at the stability of the conjugate base. Which one was more stable? Which conjugate base was more stable? The one from acetic acid or the one from ethanol? And why? These are the, you know, this is, the reason I'm going through this is normally what I would have done after class. I would have gone through and then tried to summarize everything, you know, because it's just, what it is just a whole bunch of different seemingly random observations about stuff. And what you're trying to do is you're trying to put those into, you know, an organized summary, you know. And so, if things are too neatly canned for you, then you don't really develop the skills necessary. So a lot of people say, yeah, it's very disorganized, but it's purposely disorganized because it used to be totally organized. But you know, doing this over 20 years, teaching the same class over and over again, you figure it out. You know, when I'm totally organized, you know, people don't really. I mean, they're okay for students, but to go on and be a researcher in science, they aren't going to cut it because they aren't developing those skills that are necessary in that sense, you know. And so, yeah, it is. And so, but what I want you to do is I want you to put it together. You know, because that's what you do in science. You take all these seemingly random observations that are totally all over the place, and then try to come up with some kind of pattern. It's not easy, you know. Sometimes it's very easy. You know, you see a pattern, it pops right up. But sometimes it's not. And so these are the types of things you want to do. You want to go through and you want to look, you know, why? Okay, I'll tell you why. Acetate, you know, I'm just going to repeat myself. Acetate is much more stable base because it's got delocalized electrons versus localized electrons on the ethoxide. Now, I said that earlier, but, you know, I can repeat myself over and over again, but is it going to click with you? You got to make sure it clicks. And the way to make it click is, well, I guess people can memorize this, but when they memorize this, I often get the complaint that the exam questions are nothing like the test question. I mean, the questions we did in class. It's because they just memorized one thing, one pattern. But this one, you know, you can bolster this, for example, by drawing the Lewis structure and then showing, you know, like we can see here. Here, you know, when we look at it, you know, how many times stronger is acetic acid? Well, it's about 10 to 11 times stronger. 10 to 11 times stronger is like 1 trillion times stronger than. So acetic acid is 1 trillion times stronger than ethanol. Therefore, we say ethanol is pretty much neutral. It's so weak as an acid. Most people don't consider ethanol an acid unless you're working with super bases. If you have a super base, then ethanol can act as an acid. You know, pluck that. And I've used ethanol as an acid before. It's not, you know, not terribly exotic. It's easy to pluck that proton off with the right base. And anyway, it makes this. When you pluck off that proton on ethanol, it makes a ethoxide. Now, the key difference between ethoxide and acetate is this. This is what this slide's trying to show, and this is what you would summarize. This slide's trying to show the difference between localized versus delocalized electron. So here it's going to be delocalized over 2 oxygens, giving a charge of not -1 or 0, but giving a charge of -1/2. So -1/2. Whereas you can't delocalize this into, you know, can we put that charge on the hydrogen or on the carbon? No, it's not going to work. So, well, when we have it localized, it's a lot more reactive. It's more reactive. It's going to be more unstable. And so this is number 2, the stability of the conjugate base. Now, in terms of hydration, you know, both of these are about the same size, and they both have the same net charge. You know, this is the acetate's going to have a net charge of -1 overall. You know, so this whole thing is -1, and this whole thing is -1. And so, as far as hydration goes, they should be similar. You know, in terms of hydration. And so, those are the four factors. The four factors are bond strength, right? Polarity, and stability of the conjugate base, hydration. So let's go back to this. All right, so what we do is we try to do a structural analysis of the acid strength. So let's continue with our structural analysis here. So here we look at bond strength. Well, HO versus HOs is similar. Then we look at polarity. Which one's going to be more polar, the HO bond? HOCl, the electronegativity of chlorine is a little bit higher. And so HOCl should be better. Now, about the charge localization or charge delocalization. Charge delocalization can occur in different ways as well. When I look at this looks like it's localized completely. Right? It's negative here versus this one. This is negative here as well. And so these two look the same. I mean, the charge is localized on the oxygen on both of them, right? But we have two types of charge delocalization. One type of charge delocalization is this, the resonance delocalization. Another type of charge delocalization is due to the inductive effect. And so in terms of the inductive effect, chlorine is more electronegative, so it's going to withdraw more electron density than bromine. Bromine's less electronegative. And so here, this is a secondary effect. The primary effect in charge delocalization is resonance. For sure, resonance is going to drop the charge considerably. But we also have this inductive, or, you know, this electron withdrawing effect. And chlorine's going to be better than bromine. And so here, this one will be a weaker base. That is, less reactive. Now, the more the charge is localized, the stronger the base is. And so this we would predict to be more stable, just slightly, you know, because it's not a huge effect. Slightly more stable, and then we just say weaker base. And then this would be slightly less stable, and so it should result in a stronger base. Slightly stronger base. It's not a strong base, it's just slightly stronger. And so does that back it up, what we observed here? So looking at it, HOCl is a stronger acid, about 10 times stronger than HOBr. One, it's a more polar bond, and two, it's forms a more stable product. Both of these are going to hydrate about the same. Bromine's a little bigger, and so this one, if it's a little bit bigger, it's harder to fit into water because we have to break apart more water molecules. And so as far as hydration goes, the smaller and the higher the charge, the better. Hydration. And so we want smaller and higher charge. And that leads to more stability. And so the bigger the species are and the lower the charge, the more water molecules you have to break apart. And water molecules like to hydrogen bond with each other. All right, so the difference between sulfuric acid, this is all review. sulfuric acid and sulfurous acid. Sulfuric acid would have these two terminal oxygens, but when you look at it in terms of the octet like this, it doesn't look like those oxygens would pull, because each of these oxygens is negative charge, correct? Negative oxygen, is it very electronegative? No, I mean, it already has an electron, so its electronegativity is going to go way down. But nonetheless, you know, we look at this in different ways. Just looking at the formal charges here on the octet, you can see that sulfur is indeed different. At least the charge on the sulfur is indeed different. Now, sulfuric acids and sulfurous acid are complicated in this sense. And so let's first take a look at H2SO3. When we do H2SO3, what do we have? Well, we have this structure. This structure has an octet. But it's going to end up having formal charges, a minus formal charge on the oxygen and a plus charge on the sulfur. Now, if we look at this, what's a hybridization? And so if we look at sulfur, sulfur would be what? As far as hybridization goes here. sp3. So sulfur is sp3, which means 4 orbitals. And how many electrons does sulfur have? Well, the way I fill this is, I look, there's a lone pair here, and so there's got to be a lone pair in the sp3. And then there are 3 bonds. So 3 bonds means 1, 2, 3 electrons. And so this sulfur has 1, 2, 3, 4, 5 electrons. It normally has 6. That's why it's got a positive charge. This is sulfur with a positive charge. And then the oxygens come in. You know, we have different oxygens here. Two of them are the same. And so we'll call this oxygen A here, and this is BB, that kind of thing. We'll just do BC, ABC. And so this oxygen, this sp3, comes in here and bonds here. And then we have, this is oxygen A, and oxygen B comes in with an sp3. And bonds here. And oxygen C has an sp3 and bonds here. That's that. Now, one of the things we can do is we can try to reduce the formal charge. One way of reducing the formal charge is to form a multiple bond, like a double bond. And so this is with octet. What we're going to do is we're going to expand the octet now. And so we'll just do with expanded octet. With the expanded octet, we'll have a double bond here. This. The good thing about the expanded octet is there's no formal charge, so that's good. That's good. No formal charge. All of them are 0. But it requires expanding the octet, which requires energy. You know, it comes at a cost. Expanding octet, however, requires energy. I.e., we have to promote electrons. And so let's see with the expanded octet what we have here. Go on. Well, with the expanded octet, then it's not so clear. You know, here, sulfur is pulling electrons. So when we expand the octet, then we normally do this inductive effect. This is what you see in the book. This terminal oxygen pulls electron density, in turn pulls electron density here. Pulls electron density here, causing a delta plus the hydrogen. Here, do you see the it's kind of hard, you know, because here it's just the sulfur pulling in the electron density. If you look at the oxidation states will tell you the same thing. You know, what's the oxidation state on sulfur here? You get some practice with the oxidation states, right? Okay. Well, +1, that's the formal charge. The formal charge we normally circle this. I erased it on the earlier structure. And so that's not the oxidation state, that would be the formal charge. The oxidation state would be, we'd have to count it differently. +2? No, it's not +2. +4 is correct. Do you guys remember how to do that? I know it's been a while since chapter 3. I better review it because I did it in the afternoon. Nobody remembers. The way I do it is I just box it. And so you can go back to chapter 3. It's not in the chapter. It's not in the book. It's not in the book because maybe it's more advanced, but it's so simple that everybody should be able to do it, I think. And it's just a winner take all. So sulfur versus oxygen. Oxygen is more electronegative, so oxygen takes all the electrons. It leaves sulfur with none of those. None of these and none of these. And so sulfur only ends up with 2 electrons. If you look at the periodic table, sulfur is supposed to have how many valence electrons? 6. So that means it's missing 4 negative charges. If it's missing 4 negative charges, it's got a deficit +4. Oxidation states I put in parentheses. Now formal charge is the same. The formal charge is plus. And we circle that. We circle it so that it doesn't get mixed up with oxidation state. We don't want them to get mixed up, as you can't compare the two. You either compare oxidation states with oxidation states or formal charges with formal charges. The formal charge on sulfur is +4. Oh no, not the formal charge. The formal charge is +1. The oxidation state is +4. What is the oxidation state on this sulfur here? +6. +6 is correct. Does everybody see that? It's winner take all. It's a tug of war, and sulfur ends up with nothing. If it ends up with nothing, it's lost all 6 of its electrons, giving it +6. So here we could do +4 versus +6, or we could do +1 versus +2. Here, what's the oxidation state on this sulfur with the expanded octet? +4. Do you see it's the same here as this? Both of these are +4. That's why I do oxidation state. Sometimes, you know, it's usually easy enough to do. And so anyway, which is correct? Is it that structure on the right, or is it this structure here? Which of these 2 structures is correct? Now, actually, here, I guess I should. All right, let's take a look. And so what I'd like you to do is, can you draw the orbital overlaps here? Can you draw the valence bond picture of this? This one is pretty easy. Can you draw the valence bond picture of this one first, maybe? And then this one next? Let's try that. Let's see.